preface or qualify everything he said. Yes, we met at the AI World Summit. Yes, I am a member of the advisory board. Yes, I'm about to do a presentation, but I have no clue what I've gotten myself into. So hopefully I will still be invited to the advisory board after I do this presentation. And I wanted to say also, let's see if this thing comes right up. And I got to apologize. I'm an entertainer. I do HPC AI, but work, you're studying. We work to live. We don't live to work. Unless, of course, you start your own business. Then you flip that. But the bottom line is we have to remain professional. We have to keep doing what we're doing, but there's no reason it can't be fun. Okay? And I'd much rather ask a guy for $500 million or $1 billion and have him smiling at me than frowning at me. Okay? So that's me. I'm the EMEA AMD BDM for HPC AI sales. Now, does anybody know what EMEA stands for? Wow, very interactive crowd here. Just speak up, guys. There's no hands. Because outside of the gentleman here, I'd say all you guys are 18, 19 to about 21. Okay? And then when we get to the next slide, I got to just talk a little bit about me. And then I'll show you everything I'm going to do. But EMEA, Europe, Middle East, Africa, BDM, Business Development Manager, HPC, High Performance Computing, AI, Artificial Intelligence, and then I hate the last word, sales. I'd much rather be in marketing than in sales, but it is what it is. Okay. I was born in America, come from Minnesota. There's one true football team with the word American in front of it. It's Minnesota Vikings. It's always our year until it isn't. This is another year, didn't do well. I left the US in 1984. I went to Saudi Arabia, spent 15 years there, 2 years Germany, 10 years Dubai. The rest of the time I've been here in the Netherlands. Picked up a wife, Dutch wife, born in Zaandam, met her at a British party in Saudi Arabia where I was the TA, token American, strictly for international relations. Plus, I was a bloody left-handed Yank that could beat him in darts. I had twin sons born in Germany, a daughter born in Saudi Arabia, and a boy born in Dubai. Enough. I now have a hook house at Amnes, a dog, 2 cats, and 4 kids out of the house with jobs and degrees. So enough about me. And I'm sorry, normally I have my clicker, and I like to walk around. So it's going to kind of cramp my style a little bit. But during this entire thing, please speak up. You know, this is interactive. I'm here. I'm in sponge mode, and you guys should be in sponge mode. We're going to kind of exchange information. I want to find out more about which way you're going, where your questions are, where your aspirations are. And then I'm going to invite other people that I know from other academia, Ruch, Wageningen. I can even go down into Belgium if you allow the Belgians across the border. And other Dell people to come in and talk more specifically in areas that make sense to you. But my intentions today, I want to put myself in your shoes. Oh no, I'm just going to walk here. You know, this is my first time being on this side. This is kind of cool, except during the day because I like to see eyes. I was a scuba instructor when I was in the Middle East. I used to look good in Speedos. I used to have a full head of hair. It was bleach white. I was beautifully tanned. I looked good in pink and yellow. But I ain't in that anymore. However, scuba diving and being an instructor teaches you one thing. Body language can lie. Eyes never lie. So I always like to see eyes. And when I see somebody like this, I go up to him and I said, am I boring you? And I'm also looking to see the light bulbs turn on. Because it doesn't matter what I say, it's gobbledygook until you see it in the mind's eye. And then I like seeing it. And you can always see that when you have that eureka moment. It's there, it's in the eyes. Okay, so at 24, I left the US. At 21, I had finished my college. I was smart, got to go in a year early. And I spent time, and what I'm going to do in this talk is talk about my journey somewhat. And this is me being you. And what you're seeing with me is what you can become, but what you start out with and where you end up going, who knows? You're at the beginning of a beautiful journey. Okay, I'm going to talk to you about the history of HPC, high performance computing. Okay? Then we're going to find the parallels between the hardware and the software. And I did that purposely. I want to show you the parallels between high performance computing and artificial intelligence. Okay? And then, depending on time, I'll show you what Dell has to offer. I have a presentation that I did up in Dublin to a bunch of CXOs at a whiskey distillery in the Liberties called Teeling. And with CXOs, you're dealing with the mucky mucks of a company. There you do not talk techie. You do coloring books and crayons. And I don't mean that in a derogatory sense. You got to get the buy-in on the top dudes because, you know, gravity, doo-doo rolls downhill. Okay? If you get buy-in from the top, that's a lot easier than starting with the IT guy down at the bottom and trying to push your way up. With the IT guy, you're going to do speeds and feeds. You got to know everything. But when you're talking to the CXO, is how, if I don't get this, am I going to be in business? How is this going to make me money? Things of that nature. Okay? So if we have time, I'll run you through a little bit of the presentation. But I have to use the word assume, which is the best word in the English and American language. Because to assume means what? It makes an ASS out of you and me. Whoever thought that there was a word that has the explanation built right into it? There's going to be some assumptions on my part. And it's up to you that, am I hitting the nail on the head or am I off in left field and you want me to go this way? Okay? Kind of cool, huh? Okay. You know how big my first mobile phone was? Like this. And I'm still a lot older than you, so you know you may remember back at the evolution of that. But I want to text some of your techie terms, okay? And this is kind of taking stuff off the side. Don't worry, it all folds together and makes sense. But I like going on tangents. Keeps you occupied, keeps you interested. Okay, I'm helping you out here. 1,000 we know is a kilobyte. What's this? Okay, what's this? Gigabyte? What's this? Terabyte. What's this? Petabyte. Okay, I'm gonna start separating the fools from the ghouls. Okay, what's this one? Oh, I got to put my video enhancement devices on. Which one did we say? Yottabyte? Do you think so? Okay. Okay, what's this one now? Let's try that. What do we get? Oh, I'm still wrong. Zettabyte. Okay, 3 times the charm or 3 strikes, you're out. Should we try it once more? Okay. What's this? Brontobyte. And then the last one, and the last one's name changed because I used to do this presentation when I was in storage. But what do you think this one's called? I just Googled it yesterday. Byte, but that's a 1, 30 zeros, and a bunch of commas. Okay, so you can see, no matter how smart you are, there's always something to learn. But now, I showed you this, but then look at this. Now I'm going to sit and give my knees a little bit of a rest. Okay, the global volume of data created, captured, copied, and consumed is 149 zettabytes as of 2024. And that's about 403 exabytes a day. And by 2025, it's going to increase to about 181 zettabytes. Now, okay, I can't use my gruff American terminology, but we call that a shitload of data. Okay, but this is interesting. 90% of the world's data has been created in the last 2 years. 90%. And that's driven by your Internet of Things devices, real-time data processing, Gen AI, and cloud storage. But what I like to do is let's flip this. That 90% of the world's data the past 2 years means 10% of the world's data represents everything since the beginning of recorded history. Everything. Their textbooks, all the sciences that we've learned, the architecture to build these buildings only represents 10% of the world's data. And each year, it's shrinking. So, how important is that 90%? What's it all worth? Okay, we got 90% more data, but what's it really worth? Now here, I'm going to use an example, and this example I used 4 years ago when I was selling storage. We just take a plane, 2-engine plane. It's got 2 jet engines. It's got an engine sensor on each engine. And, the thing is that when you're on a plane and an engine goes bad, you can't pull in to a place, problems, right? If you lose 2, then that's like a shark attack. Stick your head between your legs and kiss your rear end goodbye. So, what we got here is a plane. And he's got 2 sensors. Each one's taking 20 terabytes of information per hour. It's on a 6-hour trip from New York to LA. And at the same time, there's about 28,500 additional flights going on in the US. And there's 365 days a year outside of leap year. So bottom line, just a dual engine plane with this many flights generates this much data, which is in that real-time data gathering, all that explosion in information. Okay, but now I'm going to pose some questions. Is all of that data relevant?
Especially when it becomes a past data. Like it can be relevant if it is needed for a special case scenario or whatsoever.
Okay, good. Because now we're answering the other questions I haven't even put up. You were smart.
Thank you.
Everybody else, please join in. I think you're all smart, but you got to engage me. Okay? But yeah, not all of this data is relevant. Should all of it be saved? I loved storage because you have more data, I'll just sell you more. But we don't have an infinite bucket of money or an infinite bucket of capacity in order to save everything. So we have to be wise in what we save. So, how should we determine what to keep? Does anybody know of some new emerging technology that could perhaps help us figuring out what data is worth saving? You're smart too. But he also gave me some almond stuff too, so he already had brownie points. Okay, no, but the thing is, this is just using this example. But when you look at that 149 zettabytes, and we're talking about it, and real-time data collection or creation, it's a lot like this. And this is just using airplanes. Put it in any industry. Put it in a manufacturing plant. Put it in a power plant. It's all there. Okay, well, we're here to talk about a great man. This is Seymour Cray. Like his suit? This is from like 1976. This is a Cray 1. Seymour Cray is the founder of Cray Research and considered the godfather or the father of supercomputing. Now, I was fortunate enough to be about your age, and I actually worked for the man in Chippewa Falls, Wisconsin, a little hick town of 12,000 people in the middle of nowhere. But it was where Seymour was born. So I'm going to be talking about the journey here, just using this and the parallels that it has to AI. Now, Seymour was born in Chippewa Falls, Wisconsin in 1925. In 1950, when he was 25 years old, after you guys get your bachelor's, okay, but I believe he's probably got a master's, but he joined Engineering Research Associates, ERA, and he helped design the ERA 1103, the first scientific computer commercially successful. Before that, I could put a lot of stuff in there. We could talk about ENIAC, computers that filled rooms that were built just for a specific location. But, I'm going to stay with this because I find it more relevant past the point that I'm going to try to do. In 1952, ERA was bought by Remington Rand, and they started doing the UNIVAC. And then that was the big kick butt computer. But then just 5 years later, he left along with Ed Norris and a couple others. They left and they formed it to Los Alamos. Now, does anybody know what Los Alamos is? Did any of you watch Oppenheimer? Where did he build this thing? Los Alamos, Mexico. That's a Department of Energy site. He gave this machine to Los Alamos and it didn't even have an OS. But the engineers down there created an OS and showed the potential viability of this machine. It got the Cray research and supercomputing off the ground. In 1985, he built the Cray 2. Now this machine sucked a lot of power. What you got here, this love seat, there's power supplies and cooling expansion valves and EPR valves underneath here. Here is a column with 144 modules. A minus 5.2 volt on this side, minus 2 volt on this side. This is at 2,000 amps, and this is at 2,000 amps. Every time I worked on that machine, I'd have to take off my watch, my jewelry, because you get arcs. Not very good. And I could talk about the cooling. When I was in Dubai, I went with my family onto a U.S. destroyer, a Navy ship. Really cool, really cool. I went down in the engineering room, and I wanted to talk to the guy. Okay, how big a compressor do you use to cool and power the ship? He says, oh, big one, 12 ton. Pretty cool. Well, I work on a machine about almost 7 feet tall, 9 feet in diameter, and we use two 25-ton. This sucker takes the same amount of cooling requirements of 4 U.S. destroyers. Now, I tried to find the white paper, but this sucker could melt an iceberg in a day. That was pretty cool. Then he created the Cray 2, and this thing was completely different. This was a computer in a fishbowl. We did full immersion cooling, and we used floor inert. Now, floor inert is a liquid that morgues use, shove out the blood, all that stuff, get you all embalmed. But it also has a high dielectric, meaning that it won't conduct electricity, and it has a love of thermal, meaning it loves heat. Whenever we turn this sucker on, immediately bubbles. You're immediately seeing the heat, okay? We're now getting back. Now, everything that you hear about DLC, direct liquid cooling, instead of being an air-cooled supercomputer or a computer now, we're now doing DLC. That's like this, that's conduction. Now we're getting in, they're talking about immersion again, which is the Cray 2, and I got a picture of that later. So, all this stuff that we were doing in the 80s, we're now getting back to it. Excuse me? Well, oil and gas. I think it was serial number 3 or number 4 we sold to ARCO, Atlantic Richfield Oil Company, okay, based out of Dallas. Within 2 weeks, they discovered a way to pull out 2% more oil out of Prudhoe Bay. All of a sudden, every oil company wanted a Cray. and I moved to Texas to support him for a while. Then I've been to the CIA, the NSA, I've been to Lawrence Livermore Labs, I've been to Sandia, I've been to the Air Force Weapons Lab at Kirtland Air Force Base in Albuquerque. Wherever there was DOD or DOE, wherever there's a high level of paranoia, they wanted craze. And it was also going on here in Europe. And I ended up being the flyboy going out of Chippewa Falls, coming here to Europe to install these things. 2-week trip. And I was your age. But they were used, it was in scientific research places and universities, and then your government. Anything military, they loved it. Okay, and then, in 88, Seymour, he was always an engineer, but he got sucked into being the chairman of the board, that CEO, and he didn't like that. He's an engineer. So he resigned and became an independent contractor, then created a new company, and I can't remember, it's Cray something. Cray Computer Corp, and he moved to Colorado Springs, and he brought his team down there with him. Get far removed from Chippewa and start there. And at the same time, he didn't want to work with silicone anymore. It was too damn slow, switching speeds. So he started working with gallium arsenide. But it was based on a liquid immersion system just like the Cray 2. Okay? And so that was in 1988. But by 1995, they have to file for bankruptcy. Cold War was over. All of a sudden, all that military and all these things, these guys that needed this type of compute power, were no longer around. So he filed for bankruptcy. Then he created SRC. I don't know what his middle name is, but it starts with an R. It's Seymour R. Cray. He started designing his Cray 4, which is going to be his first massively parallel. And I'll talk about how many processors and stuff that the Cray's got. But then, unfortunately, he left his home, went downtown to buy a software that he was going to use to design the Cray 4, and as he was driving to work, he was killed in a car crash. So the man died, 96, but he lived to be 71, and he was a hardworking guy. Now, having worked for this man, I've gotten something called the Seymour Cray axioms, and they are as valid from yesterday, they're as valid today as they were yesterday. First one, you're only as fast as your slowest part. And you think about your AI, you guys are doing artificial intelligence. Okay, and I'll get into that a little later. You got a software algorithm running on a computer. Now, if you got a fast algorithm, slow computer, slow solution, and vice versa. You're only as fast as your slowest part. So you want to find balance. And that's still true. And then, how do you speed things up in today's physics? We're still dealing with Ohm's law, E equals IR. More power we put into it, guess what? More resistance. Wattage goes up. Need cooling. So the easiest way to do it, and it does impact everything else, is you shorten the distance between the parts. Yeah, everybody can understand that. And then, like me, I refuse to say Sapphire Rapids, Granite Rapids, or whatever the hell else they got out now. I call it Sapphire Creek, Granite Creek. And if you guys know English, a river or rapids is rapid. A creek is a little trickle of water goes like this. And I'm the AMD guy. I run circles around Intel. And the biggest thing being we're at 3 nanometer manufacturing while they're still at 7. And you think about that. Electrical signal, you're limited by the speed of light. It's a lot faster to go over 3 nanometers than it is 7. So just simple things. Then large memory matters. You can't compute until it's in memory. You can't add, you can't subtract, you can't multiply, you can't do reciprocal / divide until it's residing in memory. Then you should have a balanced architecture. I went into the bear pit one morning as a young wet behind the engineer, and I told Seymour yesterday, this guy just announced they have a CPU that's twice as fast as ours. He says, Tim, how fast is their I/O? Half our speed. So think about it. That means that CPU is going to spend 75% of its time idle, waiting on I/O. So why build it? Because you can have that super fast CPU, but 75% of all the cost is going to doing nothing. Okay? So you always want to have balance in architecture. Questions so far? Okay, so here, this is cool. Now we're going to talk techie. Okay, but don't worry, no quiz. But you're going to see how fast these machines were. Okay, we'll start with the Cray 1. Had one CPU, 80 megahertz clock. And it had 1 megaword of memory. And I'll just do this. A megaword in a Cray, a word was 64 bits. So that meant every word was 8 bytes. So 1 megaword is 8 gig. Look at that. And look, how many megaflops did we do? We did 80. And you know how much that machine cost? In 1984, when I went to Saudi Arabia with it, 50 million bucks. And we charged them 7 million a year for support, and there were 7 of us. I'm making my company $1 million a year. Did I see that money? No. But okay, but this is the first one out of the gate. But you look at it now compared to, we'll run through this, and then let's look at it comparatively to what we got today in your laptops and whatnot. In '83, we came up with the XMP. Now that's not a Seymour machine. Seymour's machines are always integers. If there's a letter in it, it was another engineering team within Cray Research. The XMP became our best seller, but it had 4 CPUs, and it had 105 megahertz clock, and they had 16 megawords and 800 megaflops.
I have a question though. Like, what were all the purposes of all of these computers back in the time?
Back in the time, it was for research. It's for all the grand challenges. Whenever you get a new toy, your physicists, your chemists, everybody wants new toys to help them solve the problems. This is a hell of a lot better than the old slide rule. And then if you remember the first calculators came out, the first scientific one was Texas Instrument. And, you had to fill the accumulator, then your operand, and then your operation. So it was mainly, okay, in the US, we were selling to Department of Defense, Department of Energy. You were selling to universities. You had Oak Ridge, wherever there was a supercomputer site. And like today, you look here within Europe, we got Euro HPC. And we're talking about this new 300 billion AI initiative where they want to build AI factories throughout Europe. Those are the people that need this power. What you're seeing today, this is the stuff that got it started. But the point I'm trying to make is look how big and fast these machines were. There's more power in your iPhone than we had in that big monster. But not back then. And it's accelerations. And when we're going to talk about this later when we try to draw parallels into AI. So then you got the Cray 2, 4 CPUs, 243, 256 megahertz, 1.9 gigaflops. Everybody's out to make exaflop machines now. We do petaflops, that's a piece of cake. Now we're into exaflops. 88, Cray 3, 16 CPUs, 480 hertz. Well, it's faster. Then we got the YMP, and I love this machine. This machine was great. We had 8 CPUs, a lot more memory, and we could do a few more gigaflops. Then we had the C90. This sucker was a beast. Each CPU processor module was this big, about this long. You had a special rack to cinch it up to put it into the slot. It was just too damn hard to maintain, but it was a screamer for the time. Excuse me? Okay, Cray 3, Cray 2, Cray 1, Seymour Cray. And by Cray 3 time, he was off in his own separate company while everybody else was doing refinement, taking the existing singular processor, putting it into 2, then working your way to 4, then going to 16, then going to 32. Always power of 2. Okay? And then 95, the Triton, last Cray I worked on. This baby was cool. You know how much a CPU cost for this machine in 1995 dollars? It was only about this big, about this fat. Take it times 10. $1,000,000 a CPU. Yeah, there's a whole cool history about that. Okay, so that's basically the last of the Crays. Now I want to put it in context. I first started working for Cray, I took care of the disk drives. These suckers, this tall, this long, this wide. And these are called DD19s. And it was a massive 300 megabyte disk drive, 22 platters. You had a cylinder with 22 platters on it, plus a servo track, and you had all the heads coming in. Head crashes, the story of my life. You're always in. And look at that sucker. It could do 3 to 5 megabytes throughput. Oh, then we got the DD29. That could do 600. Everything else was the same. But we got it up, well, still 3.5 megabytes was just higher capacity. Then we came up with the DD39, which I thought was a nut drive. This had 3 spindles in it. That's not powers of 2. I never understood 3. But it got us to 1200. It was 400 megabyte, and it could do 5.9. Then we had a DD49 where it was 4 platters, but we turned it vertically. So the disc spun this way. It's supposed to be better for head crashes because you're not dealing with gravity. And you got a lot better throughput. Then we had this DD60. All of these guys up above here, big guys. This big around, about this long. And I said, how the hell can this work? In order to be fast, it's got to be big. But then that kind of breaks the rule of Seymour saying you speed things up by shortening the distance between the parts. Yes?
What changed between the two? Because if it's a lot smaller, it was also it's a massive jump in.
These were controlled data drives that we OEM'd. These were ones that were more or less designed by Cray.
So between DD60 and D49, it's such a massive difference. It was way smaller.
But I didn't put down the timelines because, the thing is, I worked on all this stuff. And here's another thing, guys. Maintain some type of a log, a daily log, whatever you do. And you started off by doing day, month, year, space, where the hell you are. And then write down stuff because you know what? When I was your age, I'm not going to forget anything. My brain is so full now, I'm very selective about new information because that means I got to take something out. So, I honestly, I tried looking up in Google. It's getting hard to find all this stuff. And back at my brother's place in Minnesota, I got all the old technical manuals. If I had been back in the States, I'd grab that stuff and I could give you more of a history. But I only got, Jesus, I'm taking a lot of your time. Yes. Okay, I started with Cray in 81. We had the 19s, and I think in 82 we got the DD29s. And the DD60s came out when I was in Saudi. I think we got them with the YMP. I think it was about 92, 93. I'll look it up because, it's still interesting. Because, the key thing here, people, is to see whenever you start off in a new discipline or a new idea, it looks massively fast when you first start. But now look at this. I made good money back then. There was very few people that did what I did in the world. And I have very strong opinions of what a systems engineer is, but we'll talk about that over a beer. But the thing I'm trying to show you is what started everything, what started the journey of high performance computing. You look at these things. Like I say, you got more power in your iPhone or in your Android. Not that I'm biased. So you're going to be looking at also once we flip over to the software side of the house. Everything you start off with nuts and bolts and you work your way towards bells and whistles. That's the journeys of the Crays. And that took me through Europe, the US, all the spook sites, and Saudi Aramco, where I spent 15 years and met my wife. And my daughter was born in Saudi, and she can have Saudi citizenship, but I love her, so I'm not going to do it. So, but anyway, the evolution from HPC to AI represents a significant shift, as we started with building fast hardware. And once we built fast hardware and we made bigger memory, we can start tackling bigger problems. And how do you tackle the problems? By writing a piece of software that runs on it. But even back then in Fortran and your earlier languages, we could do this stuff. I've seen a huge evolution, and I want to get more into it, is in compilers. The fact that we've been able to go from SMP symmetrical, I can't even remember what the M stands for processing, scalar multiple processing, to go into x86, where we can work in clusters. And when you work in clusters, you're trying to do scale out, which means you're busting your problems into small pieces that can be run on different nodes in such a way that when they each get the answers, you can bring it together for the next iteration. Back when MPP, multiple parallel processing, started with the alpha chip in the T3D, T3E of Cray, I didn't even put that on the list, there was very few problems that we could parallelize. Everything was still von Neumann in process. Had to do A, then B, then C, then D. But through the evolution of compilers, and also I think in the languages and how they write the languages in such a way we bust it down to machine code and then you compile it and then you load it, we can do more parallel on seemingly scalar type of work or sequential type of work. So we built the fast hardware. Now we need fast software. So in the 60s and the 70s, basically early HPC systems, and you got the parallel processing, distributed computing. You guys can read that as well. And the biggest thing is getting back who used it, scientific research, weather modeling, and engineering tasks. I could put in there, and the paranoid governments. But then in the 80s and 90s, we started building faster hardware that had larger memory, more processors, and it allowed for larger and more complex problems to be solved. And then that's also when we started looking at clusters. And clusters were never built on these SMP boxes, unless you were in the DOE. They clustered Crays. But at the price of a Cray, you had to have big pockets, but Department of Defense did. This is basically the advent of x86. And once you could do x86, you're taking commercially viable small price units and then through software, building scale out and scale up in such a way that you can pretend you got a big Cray. And once they started doing this, bye-bye Cray, bye-bye big guys. But I think there's probably a DARPA project or some people are still building it for very special purposes. And who knows what Elon Musk is doing. Okay, but it is the beginning of the end for Cray research and everything else. Then, in the 90s and the thousands, once the internet really got off, and once you started getting some digital technologies, you start finding out you have more data that you can go and look at. Okay, and think about today, large language models, this lawsuits against Meta from New York Times and other ones sucking data. Okay, but you find you can get a lot more data, and then based on having a lot more data, you got to look for new ways of analyzing it and trying to pull something out that's worthwhile to justify the cost of looking at it in the first place. Okay, machine learning emerges. Okay, and natural language processing, image recognition, and predictive analytics. They become possible because due to the newer algorithms, software, on top of increased computational power, hardware. Okay? And it's always a battle. It's just like, I like to say back in the States, we had fuzzbusters. You know, we're always driving fast. Fuzzbuster is you go past the speed limit. And if there's a cop out there with a radar gun, the fuzzbuster will let you know that he's coming. This is kind of like the cops and the fuzzbusters. You know, if the fuzzbusters gets the superiority, then the cops get new radar guns. So And what we're going to be doing here is it's always going to be a pull tug between software and hardware. Okay. And then there's also the costs, because software is a lot cheaper. You don't see the tangibles. That's all built within the research and development of building the application itself. And also they had the hardware they had to purchase in order to run it. And hardware is not free, and nobody has a magic money tree behind them. You just pull out money. Okay. So then in the 10,000s to today, we got deep learning and GPUs. When Cray was bought by SGI, I worked for Silicon Graphics, and one of my jobs was professional services manager, customer education manager, and one other thing in the Middle East. But most of our customers back then, it wasn't in the HPC, it was in the visualization and these caves and things we had. And we had a system at the Kuwait Tank Corps. It was a simulator for these guys to train their troops. And the thing was broke. And it had GPUs. That's where all this stuff started. NVIDIA, most of the people that started NVIDIA, a lot of them were associated with Silicon Graphics. But, and this thing was broken. I was the guy who brought in the guys. And as a thank you, they let me try out the simulator. And you know what? If the free world depended on me, we'd be speaking Russian. Man, I would never want to be a tank driver. But that was when they found GPUs, which is built for matrices. It's repetitive parallel operations. We started that in the craze in what was called vectors. Okay. And you think about Gen AI right now, you're talking about creating vectors. Okay. And what this is continually same task multiple times. Finds out that it lends well into IT. NVIDIA started as a company just building graphics for games and shit. Now it's $1 trillion plus company. Well, it depends on how good DeepSeek does. But because of the GPUs, you're now seeing everybody, research industries, beginning to use HPC in order to do their AI models. And if I have to dumb it down to one phrase, AI, Gen AI, DL, deep learning, neural networks, any AI subset is a glorified software algorithm that runs on an HPC engine. Fast software, fast hardware, fast solution. Make sense? Okay, let's see what else. Okay, yeah. Yada, yada, yada. But what you're finding out, there's a synergy. In order to feed me more, get more data, make better large language models that don't hallucinate. And now that they got agentic RAG and all of this stuff, it's just really cool. That's going to create more synthetic data, but we're going to need systems that have the capacity to satisfy the demands of the algorithms. Does it make sense?
I have a question regarding the HPC concept. For example, we are actually comparing the capabilities of the past with nowadays. And for example, as you said, even our iPhones can be even considered as an HPC compared to the past.
Nothing's changed. It's the same concept. I could bring up a block diagram of a Cray 1, and it's still valid for today, except we don't need 800 modules to make a CPU. Everything was discrete in the Crays. We now have integrated circuits. I represent AMD, which is EPIC. We're now in the 5th generation of EPIC. I can give you an SP5. Well, in fact, I think I got something. I'll pass it around. You guys can look at it. I'll show you an EPIC chip. But this thing can have 192 cores on it. Now, that's a lot of, here you go. And that's gold now. Don't scrape it. Let me get this out of you. All we've done is shrunk the distance. We've done what Seymour says. We've shrunk the distance between the parts. We now, we're launching our 17th generation of PowerEdge servers at Dell. and I'm interested in the AMD, not the Intel. And an R7625, that's a 2RU 2-socket box, can have 292 core CPUs running at about 2.7 gigahertz. Remember the clock speeds I was showing you on that? Do you know why? Okay, this is on a tangent. Do you know why those clock speeds were that speed? There was 30 miles of wire in a cray, and everything was built to be sequential, which means when you're sending signals, they all got to get to the right spot at the right time. Because if you don't, it don't run. Now, we don't have 30 miles of wire on that chip, so you can speed the sucker up quite a bit. And our competitor has 8. And like I say, if Amsterdam was memory, and on the north of Amsterdam, you have 12 lanes to bring in cars, and on the south, you got 8 lanes to bring in cars. Which side brings in more cars? 12 lanes, duh. So everything's shrunk. Everything otherwise, it's still the same. There's been nothing revolutionary. Well, in how we create memory chips has been revolutionary. You know, we're into DDR5 now. We're at 6,400 mega transfers per second. All it takes is money. You don't want to buy these suckers. They're just too damn expensive. But, you know, all the stuff's there. And what we're doing is we're creating bigger memory. And with bigger memory, you can compute more. So the more we build it up, the more it's going on to the software side. And I'm very curious on when the actual truth comes out about DeepSeek, what they've done. Because you got to understand, you know, us Americans, we're like Rambo. You know, we kick in the door and we go, "Ugh!" That's the NVIDIA in the way we've been building shit. But now let's look at what DeepSeek's doing. You know, they've had these embargoes on them. Some of the best brains have come out of Asia. Okay, so they still have the academic smarts. And if they can come up with ways, and I don't know if it's on the algorithmic side of the house or how much it is based on the hardware, but it's kind of a tie between the two. And this brings up, and I should have put this on as another Seymour axiom. He was asked, who would you rather hire? A seasoned engineer or a kid straight out of school? You know what he said? Kid straight out of school. You know why?
Because you can train them.
He doesn't know what can't be done. You know, and that's a very powerful thing. You know, just because this is the way we've been doing stuff forever doesn't mean that's the way we should do it in the future. So think different. Do stuff like that. Yeah, we're at that point.
So, do you see Moore's law breaking anytime soon?
Well, they already say it's broke. Moore's law is no longer, yeah. And well, maybe not for Intel, but you know, for AMD, yeah, we're leaving it in the dust. The problem is we're still dealing with Ohm's law. We're still running copper, which brings in Ohm's law, E equals IR, and wattage is equal to E times I, voltage time amperage. And you look at these babies. Now I can go through, well, I want to kind of go through this next section unless, anybody got a hot date or something tonight? I'm bringing my American Express to the bar. So, you know, the thing is I always know people are more willing to participate when it's free. No, but I can show you something. We're at the cusp right now with our 17G systems. CPUs are running at 500 watts. GPUs are running between 750 and 1,000 watts in the OEM and XXM form factors, the Big 10. Okay, and your PCIEs are running about 350 watts. Now, each of these things, higher wattage means higher amperage, which means bigger power supplies. Now, when you take a rack server, it's like a 2-liter bucket. Now, how the hell can you put 3 liters of water into a 2-liter bucket? You can't. You know, we can't keep putting bigger and bigger power supplies in. So, and there's things happening in technology. And once again, all it takes is money. Pull the power supplies out of the servers themselves and provide them a bus bar, bringing the power in. So, and that's kind of like what Crays were. It's, we had the bus bars and you just hook everything into it. So getting to Moore's Law, we're at, AMD is now at 3 nanometers manufacturing. And I've always said, if you want to destroy the chip industry, you don't bomb Taiwan, you bomb Eindhoven. Get rid of the lithography machines. SML. And I got to visit, I'm going to go see their manufacturing line. Because I think it's a lot like Craze. You build it and it probably takes half a year to get it production ready to move to site. But we're at 3 nanometers. And how far can we go down before they're starting to have bleeding between circuits? And then, how much more can you put in to give it so much more? But I do know from AMD, the next gen, 6th generation, is going to have 384 cores. That means in a 2RU box, you can have 728 cores or 768 cores. Right now, we can do 384 cores in a 1RU box if you don't need GPUs. It still sucks a lot of power, but it's still affordable and you can put it in most racks. But if we talk about our big beasts, how much time do I really have, Marco? Because, are you guys getting bored? Be honest.
No.
Because I can show you some more cool stuff because it's cool. And I'll give him this presentation and I'll share it out to you because there are some links that I'd say, go ahead and check me out. See if I'm blowing sunshine up your butt falsely or if I'm doing it in the right fashion. When you turn this baby on, it takes the same amount of power as the average 23 Irish households. But now, in Ireland, the houses are made out of stone and they're windy. Here in the Netherlands, it's 28 houses. That's all taken by a system this big. That's a lot of power. But you can use this for doing training. If you're going to train your own large language model, if you were going to do a Mistral, your own Mistral, if you're going to do something like Llama, whatever, you can do your training. More than likely, most people here is you're going to be doing inferencing. You're going to be taking a pre-trained large language model, tuning it with your own data, and then using it for whatever you want. But, a lot of this is, gobbledygook, blah, 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 blah. That's marketing stuff. Whoops. Okay, this is the GPU. And in that XC9680, we got 8 of them. It's about this size. It's about this tall. But this is an air-cooled system, so it's this tall. All due to the heat sinks and everything on it. And there's 8 of them on something called a UBB board, and that takes up 4 RU of the cabinet. And then the server is a 2 RU that sits on the top. But this thing has 192 gigabytes of HBM3 memory. Now, its comparative was an A100 from NVIDIA, which had 80 gig. And remember what I said about one of my Seymour Craze axioms? Large memory matters. If you have smaller memory, what that means is you end up swapping in, swapping out, and your CPU or your GPU compute is just sitting there spinning idle while you're feeding it. But we got 192 gig. Now, this was built to go against the H100, not the H200s and not the Blackbird, or I can't remember the GB or the B200s, B300s. The key thing here, you can look at this other stuff, really cool, but it's got 192 gig. Now here, this is where I think pictures paints a thousand words. Now, a large memory model, large language model, we always talk about how many parameters you're putting on it. 70 billion. Whoa, that's a lot. How do we quantify that? Each parameter is normally single precision, 16 bits, 2 bytes. So 70 billion parameter large language model would be 140 gig. Now, based on this paper, on this link where I pulled this information out because this was done by a company that actually benchmarked this. They say you need about 1.2. You need 20% for buffer, scratch, yada, yada, yada. So you need about 168 gigabytes for 170 billion parameter large language model. So I show a comparison. We have a box called the XE9680, which I talked about. And you can have 8 NVIDIA or 8 AMD GPUs. Now here, to do 168 gigabyte, 70 billion parameter large language model, I can do it on one MI300X, but I need 2 H100s. So what if I run 2 of them? And just lo and behold, this is what happens. I can run 8 70 billion large language model inferencing, fine-tuning, whatever, 8 instances in one single box, whereas if you're going to use NVIDIA, it takes 2. Or do we steal the power from 23 Irish households, or do we steal the power from 46 households? Plus, $500,000 versus $1 million. Now that's just looking at those large language models. But now let's say you're doing inferencing. You're not going to do it on a 70 billion. Say you're going to run an MS Copilot, you're going to run a chat bot and stuff. You don't care about hallucinations so much. It's like most chat bots with all these help desks. You ask them something and, it hallucinates. But, they run lesser parameter, okay? Like 7 billion parameters, kind of like a standard, and they're even making it less now. But if we take this, what's very interesting, one MI300X, we can hardware partition into 8 chunks. 8 hardware partition. NVIDIA has to do a software partition, and they can do 7. And that drives me nuts. We are in a binary world. 1, 2, 4, 8, 16, 32, 64. Where does 7 come in? It doesn't. That also implies why it's a software. And with software, whenever you do something, that's a fancy word for latency. And latency is the biggest swear word in computing, HPC, because that's a fancy word for slow. Okay? But the biggest thing here is what we can do. We can run 64, 24 gig, which means 12 billion parameter, versus they got 10 gigs so that they can run 5 billion parameter, but they can only run 56, and you end up getting that. Were you going to ask something?
Yeah, what happens there? But why can they partition 8 instead of NVIDIA as well? Why there's like 10 gigas left over?
Well, no, they have an 80 gigabyte, and 80 divided by 7 gives you, and I put 10. Okay. Whereas we're 192 divided by 8. So, you're limited by what you physically have. You can make things look bigger, like a batch environment, by oversubscribing. But then when that happens, that means you got to take stuff out of memory, and that's called swapping. And you put that to a swap disk while you swap in the next load of work. You get your time in the machine, then you do another swap. And so, anytime you submit a batch job, you hit submit, but you don't know when you're going to get it back. And when you get it back, the wall clock time, how long it actually took to run the job from when I submitted. And then you'll also get the actual execution time, which is significantly less. So the larger hardware you got, the more work you can do. Hence, you can shrink your wall clock times. Okay, now there's a software stack. The key thing is AMD has embraced open systems, meaning no software licensing. It's based on ROCm, whereas, NVIDIA's got CUDA, and CUDA, basic use of CUDA is free of charge. If you want to do something special, any bells and whistles, all it takes is money. Now, this just basically shows the software stack. Okay, we got the hardware on the bottom, then you got the ROCm environment where you got all the pieces that you require. Then you got the ecosystem up there, your various languages, PyTorch, TensorFlow, Triton, all those guys. And then all that stuff feeds up into a product that people can hopefully make money with. like your chatbots and what have you, or any type of service. That's kind of the software stack. Now, the biggest thing like I want to show here is, I'm doing battle against NVIDIA. So I got to talk about NVIDIA. And what we got is it starts with your libraries. If there's a CU on a library, that's CUDA. If you look, for every CU library, we got a ROCm equivalent, or ROC equivalent. So we mimic the libraries. Then, if you're written in Triton, if your code is Triton, the source code, Triton code, can be compiled directly into HIP and to run on ROCm, or it can run on CUDA. If it's CUDA kernels, you run it through the CUDA compiler, and then you can execute it on NVIDIA. What we have to do is we take the CUDA code and we run it through something called Hipify, which is glorified Perl translator, and it takes CUDA and translates it to HIP. 95% of the time, it doesn't change anything. It's exactly the same code. And then you run it. Now, if it doesn't change, performance 95% of the time is going to be good. But it depends on how smart the programmer was. Does he understand, memory is a precious resource. Writes are expensive, reads are cheap. And then when you get to memory, how do you reserve memory to do a write? How much of the memory do you freeze up in order to do the write? And then if you got banks, if you got sections, you learn to stride memory in your writes in such a way that you don't lock the system up. Now, based on the way NVIDIA memory is, their HBM3E memory is, the way they stack, and compared to us, banking and stuff can be different. So that's where you're going to possibly see some performance increases, but that's in about 5% of the time. It's really in your nerds that are really getting down into the heavy and the dirty. And once you get up into the frameworks like Python, hardware becomes an abstract. Because when you're up there, it's like calling Uber. You don't care what car it is, you're getting the service. And when you're writing up there, you don't care. And then that's where the hardware advantages of having larger memory should give you appreciable speed ups.